Welcome to the Entangled Show, a weekly conversation where we bridge the gap between high-level physics and everyday reality. I'm your co-host, Pete Codella, streaming from Utah's Salt Lake Valley.
And I am Sumit Parashar. I am from Bhilai and live in Lehigh. I live in two places at once, just like a quantum particle. I coined the term Quantonomy, which is what this show is all about. Thanks for joining us.
Sumit, good to see you again.
Morning, Pete. Great to see you.
Excited to talk about our topic today of probability.
One of my most favorite topics, a lot to talk about. I think we have a good set of slides and content to share with you. But Pete, as we get started, I would love to take a step back and introduce or reintroduce our viewers and our listeners to you. I know that you've had a tremendous career so far, and then sky's the limit for you. But I want you to take a second and talk about yourselves and share with us.
Well, I'm happy to answer some questions, and I guess I'll go along since probability, like we introduced before, Pete, probability, we'll start with P, so let's do it.
Awesome. So when we met the last time, it was at a meeting in Salt Lake. And at that point in time, you were working with the governor's office and you were the managing director there. And you did a whole lot of projects there. But if you can elaborate on that part of your career for our viewers, that'd be fantastic.
Yeah, I never set out to become a public servant, to work in the governor's office. The opportunity came over 7 years ago. And I joined initially as the communications director in the office. And in 2022 was promoted to be a managing director over the business services portfolio. And it was really awesome to see how the state works to support small business in the state of Utah. I was the liaison to several other public-private organizations, to the Small Business Administration for the state. And there are a lot of programs and a lot of opportunities for small businesses in Utah. Our economy here is driven by small business. It's like over 99% of people in our economy are employed by a small business. We are also a diverse economy, meaning we are really closely aligned with the United States economy as far as the different types of industries and things. So it was an honor and privilege to work for two governors and for executive directors. It's really cool to see what the state does to support small business. And
beautiful. And Pete, I know that you haven't shared all of what you did there. I think in one of the episodes, we'll go deep diving into your accomplishments. But my salute to you and to the governor's office for supporting small businesses because I'm a small business owner. And so I know the kind of support that we get from the state. One other quick thing about you, and then we'll move on to probability, is that what got you interested in cooking?
Cooking, interesting. I do like to bake. I have a side hustle called Pete's Treats, where I'll bake cookies and take them to different events. When I was a teenager, my grandparents would come visit us. At the time, we lived in upstate New York. My grandpa was named Angelo Codella. He and my grandmother's sister and husband, they had a restaurant in the Las Vegas Valley for many years. And my grandpa taught me how to make an Italian ricotta cheesecake when I was a teenager. And that just kind of introduced me to cooking and baking. And I have a sweet tooth, anyone will tell you. Over the years, I've just developed a repertoire of different recipes and cookies that I really like. And maybe one day we'll bake some cookies for some of our listeners.
That would be awesome. Talking about all of those cookies and food got me hungry. One other quick thing is that we met at, I think it was one of the major government offices in Salt Lake. But when we met, we talked about a whole lot and we knew that we would be working together one way or the other. But at that point in time, I did not even know that we will be hosting a show like this together.
Yeah, what was the probability of that?
Thank you. Those were exactly the words that we were going towards. What was the probability like? But the probability was non-zero. We should see the word. So from an optimistic person's point of view, the probability of hitting a goal is always a non-zero. And so a series of coincidences occurred, and then here we are talking to you about probability and quantonomy.
I love the comment that you miss 100% of the shots on goal that you don't take.
Absolutely. That is so true. That's it, Peter. Let's dive into the topic of the day. Today we are going to talk about probability. Of all the words that describe behavior of quantum objects in quantonomy, there is a very good probability that for us to understand probability with reference to quantum objects is easier than the other topics. We talked about superposition. We are going to talk about entanglement going forward and a lot of other quantum phenomena and behavior. But probability, as it pertains to quantum probability, should be an easier topic to discuss. So this is a visual all of us are familiar with, except for the people who have just been listening to our podcast, which is why Pete keeps saying is that, hey, please come in and look at the visual part of it through YouTube too. But astronomy versus quantonomy. I will not go into details of the slide because we are familiar, but I will change the orientation of the visual a little bit. And as we have said, astronomy as is above, quantonomy as is below. So this is a better oriented visual when it comes to that maxim.
And again, our listeners, viewers may not be familiar with quantonomy versus astronomy, but it's a term that you've coined that basically describes the study of quantum existence in our reality. So we're promoting quantonomy to become a word that we use as part of our lexicon.
I skipped over that. In the first episode, we went into detail, but absolutely. So that leads us to this visual where we will look at it from a slightly different perspective and we will start diving into why do we need probability or why do we need to study probability. So if you look at it from that perspective, you have macrocosm as is above, you have microcosm as is below. And this visual describes waves coming in from the left side. And from an observer's point of view, which is me or Pete, now we are looking at it from the right-hand side and it becomes particles. So that describes the wave-particle duality when it comes to the microcosm at the atomic and the subatomic level. Taking a step back, we wanted to draw parallels from the real world on what waves are. How do we as humans coexist with waves? And so the visual I have right now is about a Wi-Fi router. So we have a room. It's a beautiful room with a couple of TVs and there's an iPad and some Apple devices. And the Wi-Fi router essentially is throwing out waves that these receivers receive. And hence the receivers are talking to the router. Now, in the real world, the way it works is that I see the router, I see the room, I see physical manifestations of all the particles in that room. However, I do not see the waves. Right, Pete? Do you think this visual is a good one to describe the invisibility aspects of the waves around us?
Absolutely. I mean, Wi-Fi is something we're all familiar with now. And I think back to, technologically, as we've advanced, we discovered radio waves, right? We discovered broadcast waves, internet, Wi-Fi is what we're familiar with now. It's funny, our young drivers on the roads don't memorize directions. They just put it in the phone. And when I travel with my parents, they always will explain how to get somewhere. And I'm like, it's right there on the map. You don't need to explain it. I know where to go. Anyway, that's a digression. But people are familiar with different types of technology. They have to travel through the air. They have to be in waves for us to receive them. And it's a matter of us being able to tune in to the right frequency to get the right reception, which goes back to my experience in public relations and communications. There's a sender, there's a receiver, and all the stuff that happens in the middle, that's the frequency. And hopefully you're attuned to the same frequency. And if not, there's a miscommunication.
Beautiful. I love that example. Even the example for the navigation that you're talking about, it is not a digression in any way. It is a real world example of a device receiving information over waves and then that device converting that information to something that is actionable from a human perspective. So we are looking at the visual, the waves are depicted as something invisible. Here, I want to emphasize something that will bring us to a point where we don't have a lot of answers on why this actually occurred. But I'm just going to state what we have as of right now. In the real world, in quantum reality, there's an observer's paradox, is that we don't see the waves. We just see the particles. So it goes back to the measurement problem is that behind us, there could be a lot of waves going on. But then as we turn around, observe them from a system to a system level, they actually become particles. So that's part one of the explanation. Part two is we don't see the waves, but we hear the waves all the time. We have five senses, all of them work differently, but there's a distinct difference between the way we see and the way we hear. When we see, we don't see waves, but we cannot hear anything without the waves going on. So it's a built in paradox in our bodies.
I love the example of the multiple senses we have. And I think of people who may be deaf or blind and how their other senses will be amplified and even pick up more. And I feel like our whole discussion on quantum is about a fourth dimension, more senses that are out there that we just may not recognize.
Beautifully said, Pete. I'm thinking of the next topic, which is entanglement. When we get to that, I think a lot of this will come into play again. But on the topic, going back to waves and particles, we as humans don't see waves, we see particles. But there is another sensory perception of hearing that works just on the basis of waves.
And it's a good thing we don't see them because that would be sensory overload, like this shows.
Exactly. That's the point, Pete. Is that imagine how crazy the world would be if I were able to see all the waves going around me. I mean, I would not be able to focus on anything. You have these waves, or you have all kind of wave with a kind of frequency. You have the universe is bombarding us with waves all the time. There is no nothing that we know of. I mean, this is a philosophical statement, but also a true physical statement. Is that there is no nothing. There are things between us and the laptop, and even the space is something. So the space is full of waves. And if we were to see all of these waves at any given point in time, it would be a bad thing for us and we would not be able to get anything done.
This makes me think of a science fiction movie where people can read each other's thoughts, telepathy. I feel like it functions on some kind of wavelength that most people don't recognize.
Absolutely. When we get to entanglement, that is something we'll talk about. We will make a prediction saying at some point in time in the future, someone will connect telepathy to entanglement. And that's a beautiful topic. So the slide talks about how we would be having a sensory overload if we were to see all the waves. We are actually fine-tuned not to see the waves. So fine-tuned is a big word. This is a little aspect of fine-tuning for humans. As we talk about astronomy and connect that to quantonomy going forward, there is a lot to talk about. But at this point in time, what I want us to know is that we consider ourselves as fine-tuned human beings, and no pun intended. I think this will come up again very soon.
Another thought I've had is like animals in the sea that can know where things are by sonar, or bats flying through the air, right? Different
Yep.
species fine-tuned in a different way.
Beautiful. So on the topic of probability, this is the core slide. I mean, this is the key takeaway for all of us, is that when talking about quantum probability, what we are looking for is the answer to this question on where is the electron, or where is the proton, or where is the subatomic particle. So I have an electrical engineering degree and a background. For me, from an electrical engineer's point of view, knowing where the electron is of high significance. You can flip an entire system on its head if you just change the location of an electron, or if you change the flow of the electron from one direction to another. So worlds depend on, and systems depend on knowing where the electron is. We give a lot of significance to determining where the electron is. Now, based on quantum behavior, we know that you cannot exactly predict two aspects of an electron at one given point in time concurrently. So the first aspect is the location on where the electron is. Or the second aspect is momentum, or the mass and the speed combo, which is momentum. So the rules of physics prohibit us from knowing both of those aspects about the particle at a given point of time, which is why probability comes up to be one of the biggest aspects or biggest concepts behind quantum.
Speaking
Uh,
of these particles, it's reminding me of MRI machines, magnetic resonance imaging. Is that something that flips these and then you see an image?
So you are right on the dot. When we're talking about quantum probability, the particles and the magnetic resonance imaging machines. Taking a step back, there's a way to take a photograph of a body and going deep within and finding out the mechanical structure of a body, which is you can use X-rays for that.
Yeah, I was
Yeah.
thinking we were talking about different machines that are on different frequencies and show you different things. X-rays for bone structure and MRI for the soft tissue.
Beautiful. The application of MRI is you can get into a body in a non-destructive kind of a way and come back with a 3D image of how that body is structured. MRI is mostly on the brain scan side, is that, of course, you can't go deep diving on what's going on inside the brain. And so you have to stay out. It's a non-destructive way of imaging how the brain works. And there is a direct correlation between the probability principle of quantum versus MRI. So you were right on the dot when it comes to that particular example. I want to bring up another very simple example in terms of trying to explain what quantum probability is the example of a bus. In our macrocosm, which is our level, we know how buses work. We know where the bus stops are, and we can, with a fairly high degree of probability, predict where a bus is going to be at a given point in time. Even in Utah, we have good amount of public resources and buses, and we know where a bus would be at a given point in time. One extreme example is in Japan. You could predict at a 99.9999% level where a bus would be on its given route. They are so very disciplined when they're on the public infrastructure.
It's making me
So
think of airlines in the United States, and maybe the probability of an airline being on time will influence my decision to buy a ticket on a specific airline. For example, I believe Delta is more on time and can predict their airplane schedule better than Frontier Airlines.
I agree with you. We live in Salt Lake. There's a hub here. And I had the opportunity to actually have a discussion with Ed Bastian on Delta's schedule at one given point in time. So I'm proud about that. And I will never ever say anything negative about Delta.
And we are not sponsored by anyone or anything at this point.
Not yet, but we need to call out Delta on this.
There you go.
So coming back to the example, in the real world, we can make a fairly solid prediction using probability principles. However, when it comes to the quantum world, probability works in a very different kind of a way. So in this visual here, I have a loop where I'm describing the bus goes. So it's the bus's route. In a way, we can bring in the lesson learned from the last episode, which is superposition, and try to describe this visual. Is that you have a bus, it's supposed to be on a route. And if we are not observing it, it may be in all of the spots at once and we don't know about it. But as soon as you take a measurement or if you observe the bus pretty much shows up on a specific location. But coming to the topic of the day, which is probability, if you are not looking at the bus or the route, we know that it is in superposition, but also while being in superposition, you can point to a certain location and ask the question saying, hey, if I'm looking at this particular bus or this particular location, what is the probability that the bus is existing at this location at this given point in time? So this is, sort of another way of describing what quantum probability is. I'll quickly move on to a pretty interesting topic from our perspective. Is that on the visual, I have Albert Einstein on one side and I have Niels Bohr on the other side. And when it came to probability, Albert Einstein refused to believe that this could be a principle that applies to day-to-day life. But then in hindsight, we know now that probability as a concept has been proven beyond doubt. So it works, it works, it works. So, but at that point, when just around the time of Copenhagen interpretation, Albert Einstein famously said that God does not play dice with the universe. On the other hand, Niels, and you can pretty much tell how sharp these gentlemen were, even in their comeback, because Niels Bohr came back with a comeback and said, Mr. Einstein, please don't tell God what to do. So I think this is a good visualization of what they were thinking of probability. And so, Pete, what do you think about this?
I don't know if you've noticed, Summit, but I feel like we as humans like to tell God what he can and can't do. And it's probably not our place to do that.
That is so true. That's again, you said it in a funny way, but it's a deep topic. And like we talked last time, we will definitely, as we learn these fundamental principles of quantonomy, we will converge on a point where we will talk about this. But we will bring up this slide again and we'll drill down on that topic again. But one more quick observation about this topic or the back and forth between Albert Einstein and Niels Bohr that, in our opinion, they were the yin and the yang of quantum. You definitely need friction to be able to make progress. The scientific community is really strong in terms of argumentation, and the scientific community wants real proof. Anyways, I love the way they kind of interacted with each other, shows the kind of friction they had going on with each other too, but in a very positive and a good kind of way. On this slide, we'll just begin to recap what probability is. It's a busy slide. There's a lot going on here. We have titled it The Guide to the Subatomic World. So we are talking about the basic principles of quantum again. So recapping what we talked the last time is that superposition is a fundamental behavior property of quantum objects in the microcosm. Objects can exist in multiple locations at once or multiple positions at once. When we observe, we force the system to make a choice, and the particle shows up in a specific location. And the bottom line, literally the bottom part of this slide, says the reality that we live in at this point in time is fundamentally probabilistic. Is that when we force a system to take a form or take a shape, and we force it by making an observation of the system, it shows us version. And Pete, bracket on the version part of this statement is that there are bizarre and spooky consequences beyond our imagination at this point in time in terms of how probability could be playing a role in our day-to-day lives. Quick detour is that could infer the theory of probability actually infers that there are multiverses surrounding us.
That's a pop culture reference for me, the Marvel universe and the multiverse. If you want to think about superheroes existing in different forms and different types of reality, the multiverse is a good example of what we're talking about.
And Pete, in my opinion, at this given point in time, knowing what we know, it is not just a pop reference. There will be a point in time where, because of indirect observations, we will come to a conclusion that we exist in a multiverse, and these principles indirectly point us in that direction.
So could another reality be one's free will? In other words, do we really have agency and free will, the ability to think about things, or is it just complex and random? I don't know.
Me neither way. My opinion is that I'm an eternal optimist. I know that things work out and will work out. And so, from our personal perspectives, just the fact that the laws of quantum say that the universe is probabilistic, it's a very good thing for me. I know that if we set out to do something, and even if it has 1% probability of succeeding, it's like we ignore the 99% of the probability where it is not going to work, just focusing on the 1% that's going to work. That is such an optimistic thing for us. So I'm on the side when I agree that the probabilistic principles are true. And then I also agree that there is never a 0% probability of every potential. So it's a deep topic.
My mind's also going, and I'm probably going to get the movie wrong, but to the Star Wars franchise and the pilot who has the robot who says the probability of success is, and he's like, I don't care. Like he's always going against the probability of success. And someone can fill in the gaps on which movie and which characters I'm talking about, but I can see the conversations in the cockpit in my mind. Okay, the movie is Rogue One, and the characters are Cassian Andor, the pilot, and the robot is K2SO.
Beautiful. And it's a pretty optimistic way of going about things, so that when somebody asks me to do something, we don't come back and say, hey, there's a good chance that we'll get it done. A lot of times people come up and say, yeah, let's get this done. The other thing this slide talks about, the influences or the bizarre and the spooky consequences of what we are just talking about. We've had so many people with high IQs looking at these fundamental properties of quantum objects. And they're like, if X is true, then Y must be true too. They've come up with a lot of scenarios that seem improbable right now, but are true just because we have proven that these properties work, that we know they work right now. One aspect of this slide is we have brought in a diagram that talks about wave-particle duality. Mr. Young, way back when, came up with double-slit experiment that opened up the subatomic world to us. The bizarre and the spooky consequences of that experiment are something that even we have not come to terms with, even in the 150 years after that experiment was first conducted. There are so many permutations and combinations of the double slit experiment being conducted as of right now. It's beyond our apprehension. One other aspect that I referred to just a little bit when I was describing the position of an electron is that there is an uncertainty principle written by Mr. Heisenberg, where it says that at any given moment in time, we cannot have these two attributes of the electron determined 100%, which is position and momentum. They are mutually complementary to each other. If you know the position of an electron, you can't tell what the momentum is, and vice versa. Is that if you know the momentum of an electron, which is kind of creating a cloud around the proton, is that there's a probability of an electron being in a position. I want to say that position and momentum are mutually complementary in this universe, and you can't predict both of them together.
Something I'm thinking of as we're talking about this, the Winter Olympics in Italy just kicked off as we're recording this. And I'm thinking of athletics and position and momentum. And there's an example from a few years back with a hurdle runner from my alma mater, BYU, was in a race, steeplechase, I think is what it's called, and fell over a gate and was just in last place. So he was up towards the front of the pack. He tripped, he fell, everyone passed him up. He got up. In his mind, he had rehearsed, hey, if I fall, I'm just going to get up and run. I'm just going to keep going and not quit. And that's what he did. And he came back to win that race. It's a really cool example. And the commentators were just amazed. They're like, wait, here's this runner from BYU. And he just kept moving up and eventually won the race. But that position and momentum reminded me of sports.
Beautiful. So he pretty much picked up on that 1% probability that he could still win and converted that into reality. So he manifested reality based on a dream or the vision that he had before. That's a beautiful example. I love it. The last thing on this slide was about the entanglement. And we have the next episode coming up next week where we will go deep diving in what entanglement is. And that's the reason why I will not go deeper into this right now. This is the last slide for the day, or the last visual. It is pretty busy. And, I wanted it to be up here because it does talk about some mathematical notations of how probability actually works. One aspect that we can actually introduce to the audience at this point is the Greek alphabet. On this visual, we have Psi showing up a couple of times. And one thing that is not showing up is any equation. We have promised our viewers that we will demystify quantum and we will, make it easier. And so based on that promise, I have stayed away from bringing in any equations, which might throw off a few of our audience.
But just because we're not showing the equation doesn't mean that it doesn't exist.
I love the way you said that. It does exist. When we begin to observe it, it will show up in our realities. Well said. Yeah, this slide goes into the details of how classical certainty versus subatomic uncertainty comes into play. There is a probability of something happening, and then the moment we observe it, it clicks and it manifests itself. While doing all of that, position and momentum of that particle could not be determined at one given point of time concurrently. There's a lot going on in this slide, but I did want to bring it up for viewers who want to pick up quantonomy as a detailed topic that they want to study or they want to go deeper into.
Chance and probability is reminding me of one other thing from almost 20 years ago. We have two children, they're 4 years apart. When our son was 1 and 2, the four of us would be at the table, and almost every meal, I'm not kidding, he would take something, a piece of food, something, and throw it, and it would land in one of our glasses of water or cups. Like he almost always would, what is the probability? And then it would make a big mess. And I mean, it was crazy.
Sweet. And that's how we learn. We see things around us on a day-to-day basis, and that's how we learn. So that's it for today.
Let me ask you one more question. How is quantum probability different from other probability?
It is, in my opinion, the same.
Okay.
This is one of those words in quantum studies, quantonomy, quantum mechanics of physics that I would not change. For example, we brought in the new word quantonomy because they realized that quantum physics, quantum mechanics, quantum biology, quantum chemistry, quantum gravity, there's like a million topics that need to be brought in one umbrella word. That's why we created quantonomy as a word.
Good point.
Superposition, again, I have a new word. We need to brainstorm it within ourselves before we announce that word. And I'm preparing kind of a back and forth with NIST on that word too. But we will make a solid alternative word for superposition and at least present it to the groups and the agencies who approve words in the scientific community and see if they approve. Probability and entanglement. I would not change these two because these two words say what they do in the classical world and in the subatomic world is that they allow us to predict something. Now, the prediction could be, for example, on the last episode, Pete, you talked about your favorite sports team, whether using quantonomy, it will be possible to predict. And I said, yeah, that's something that we'll talk about in the next episode. So here we are talking about that.
It's also making me think of the movie Moneyball and the data scientists who put down all the information, right? And all the data help predict what was going to happen with the different players in baseball.
Beautiful. So to answer your question, probability is not a word. There is at least one zero probability that we're going to talk about in this episode is that the probability of us recommending a word against the word probability is zero. So we are happy with this word. It is the lingua franca. And, if I speaks about this to my daughter, I know that I can explain her probability from a classical perspective and also from a quantonomy study perspective.
And again, in the year 2025, what was the probability that Sumit and Pete would launch the Entangled Show as a podcast? Wasn't zero, wasn't 100%. It was somewhere in there, but we didn't know. And here we are in 2026 having these conversations, which hopefully help our listeners think about things in a new way and maybe learn a little something along the way. So that's probability. And next week, we get to talk about our namesake, entanglement. Any parting words?
I love this. Pete, that we started out writing scripts for these episodes, and then a lot of times we still do. But yeah, I mean, there is definitely a vibe going on, and both of us get into a zone when we talk on the show. So the scripts go for a toss, and then we just have fun during the show.
Fun for us and hopefully for our listeners. And some people might think we're really nerdy.
No, the thing is, from that perspective, we agree that both of us are having fun. And then also in the last couple of weeks or so, we are definitely getting good vibes that a few of our listeners are tuned in and, they are having fun with us too. And I'm happy to think that there is a there's a probability that there's a good amount of probability that they are actually having fun with us. And between you and me, Pete, I'm honored to be a part of this show with you, honored to co-host this with you, and really honored to have you as my friend.
Me too. Same here. Thank you so much. And to our viewers and listeners, we'll catch you next week.
Sounds good. Thanks, Pete. Bye.
The Entangled Show podcast is available on YouTube and wherever you get your podcasts. Please like and subscribe to the pod. Connect with us at entangled.show or send an email to info@entangled.show. I'm Pete Codella. Thanks for listening.
I am Sumit Parashar. Signing off for now. Thanks again for joining us here at the Entangled Show. We'll see you next time.